Hello everyone, I'm Lipu Zhou. Today I'm going to introduce our work, Efficient Second-Order Plane Adjustment. Planes ubiquitously exist in man-made environments, so planes are generally used in 3D reconstruction for depth sensors such as IGPT cameras and LiDARs, as demonstrated by the following examples. This paper focuses on the problem of estimating optimal planes and sensor poses to minimize the point-to-plane distance, referred to as plane adjustment, or PA. In PA, planes and poses are jointly optimized. Planes are the counterpart of points in bundle adjustment, or BA. Thus, the well-known solutions for the BA problem can be directly applied to the PA problem. But the PA problem has its own characteristics. We present an efficient second-order optimization algorithm for PA. Here we use a simple example to introduce the characteristics of the PA problem. In this example, we have 4 planes and 3 poses. We want to jointly optimize these variables. We can use a factor graph to summarize this problem. This factor graph is similar to a BA problem with 4 points and 3 poses. But unlike the BA problem, the planes in the PA problem have a closed-form solution given the poses. Thus, we can simplify the factor graph like this. The benefit of this characteristic of the PA problem are twofold. Firstly, we can significantly reduce the number of variables. In this case, the number of variables is reduced to 3. Secondly, we can ensure to obtain the optimal planes when we update the poses, which leads to faster convergence. However, it is challenging to compute the Hessian matrix and the gradient vector of the resulting least squares problem. This paper solves this problem. We provide the closed-form solution for the Hessian matrix and the gradient vector. Let us start with problem formulation. Assume there are n planes and n poses. Here, pi I represents the ith plane and xj represents the jth pose. Assume pi I is observed at xj, which generates a set of points, Qij. Assume Pijk is a case point in Qij, and Dijk is the distance from Pijk to the plane pi I. Using these notations, we can formulate our cost function like this. Here, Ci represents all the cost on the plane pi I. Let us use a simple example to explain this cost. Here we have 4 planes, so we have 4 Cs. Each C is the sum of squared point-to-plane distance. C has a closed-form solution. Assume M is the scatter matrix of a set of points on the plane. C is equal to the smallest eigenvalue of M. Using this fact, this cost function can be written as this. This cost function only depends on the poses. To minimize this cost, we have to derive its Hessian matrix and gradient vector. We first consider how to compute lambda I3. Assume the plane pi I is observed by the poses in a set of xi. Lambda I3 is the smallest eigenvalue of the scatter matrix Mi. It is the root of this third-order equation. Here the coefficients Ai, Bi, and Ci are functions of the poses in xi. According to the implicit function theory and the chain rule, we can prove that the first and second order derivatives of lambda I3 with respect to pose xj and xk as fall in equation 24. These derivatives depend on the first and second order derivatives of the coefficients ai, bi, and ci with respect to the pose xj and xk. Here the coefficients ai, bi, and ci are polynomials with respect to the elements of Mi. Theory 2 provides the form of Mi with respect to the pose xj alone and both xj and xk. With these formulas, we can easily compute the first-order and second-order derivatives of the coefficients ai, bi, and ci with respect to the poles xj and xk. Assume axj and bxj(xk) are one of the elements in mi xj and mi xj(xk) respectively. Using theory 2, we can easily write axj and bxj(xk) as this. Let us first consider the first-order partial derivative of axj. It has the form like this. Let us define x0 for xj equals to x0. This matrix can be easily computed. Similarly, the derivatives of j with respect to xj and xk can be easily computed when xj and xk equal to x0. Note that we only need to compute the derivatives of h and g at x0 once and reuse them in the following iterations. We can easily make the iteration stay at x0 for each pose if we update the following variables in this way at each iteration. We summarize our algorithm in algorithm 1. At each iteration, we first compute the Hessian matrix and the gradient vector. Next, we conduct the damped Newton step. Then we update uij and pij to make the iteration stay at x0 for each pose. We collected 4 datasets to evaluate the performance of different algorithms. For each dataset, we adopted 4 Loy levels to perturb the trajectory. The results show that our algorithm can significantly outperform the state-of-the-art solutions. We've also tested the case that additional Gaussian noise with the STD delta pt equals to 0.05 meters are added to the NIDA point cloud, and the poses are perturbed by Gaussian noise with delta r equals 3 degree and delta t equals to 0.3 meters. The experimental results show that our algorithm can significantly outperform the state-of-the-art solutions. To summarize, this paper presents an efficient PS solution. Our algorithm takes advantage of the fact that the optimal planes are determined by the poses, so that the number of unknowns can be significantly reduced. Furthermore, this property can ensure to obtain the optimal planes when we update the poses. The main contribution of this paper is a closed-form solution for the Hessian matrix and the gradient vector for the PA problem. Thanks for your attention.